That is the fact that is the question of how we can describe black hole formation and subsequent evaporation in a way that is both unitary and consistent with some notion of locality and causality. That's not what I'm going to talk about. I wish that I could, but I have nothing profound to say about that except that it's a mystery. So instead, I'm going to talk about three other puzzles involving black hole thermodynamics that are interlinked and that, again, I don't have an answer to, but I have some suggestions and some hints of a direction to go. These three puzzles are, first of all, why is entropy proportional to horizon area rather than, say, volume of a black hole? Second is the question of why the proportionality factor is always the same, no matter what kind of black hole you're looking at. It's always a quarter of the horizon area in Planck units. And the third puzzle is why there are so many different ways of counting different black hole degrees of freedom that nevertheless manage to come up with the same answer. So let me go into these a little bit more in detail to begin with. The first problem is this area law, the fact that the Bekenstein-Hawking entropy is proportional to area, while for almost every other system we know, entropy is an extensive quantity, it's proportional to volume. Now, this isn't a contradiction. You can't take a black hole and cut it into two subsystems and ask how to add their entropies. But it's a puzzle, especially if we want to explain the entropy in terms of microscopic degrees of freedom. It's not obvious why the number of degrees of freedom should depend on the area and not the volume. The other two puzzles are both forms of what's sometimes called the problem of universality. To start with, pick your favorite black hole in any dimension you want, work out its entropy, then give it a charge, an electric charge, a magnetic charge, any kind of other long-range charge you can think of. Start it spinning along any axis at any angular velocity. Distort the horizon by putting pieces of matter around it that gravitationally change the shape of the horizon. If you are in higher dimensions, you replace your black hole with something else that also has a horizon, a black string, a black ring, a black brain, a black Saturn, which is a black hole surrounded by a black ring. Even look at other kinds of horizons like the de Sitter horizon. Calculate the entropy and you always get a quarter of the horizon area in Planck units. This is very peculiar. Why should it be that even if you have a black hole and you somehow stretch the horizon, that doesn't change the entropy? The third puzzle has to do with the attempts in quantum gravity to actually explain entropy in terms of microscopic degrees of freedom. Now, we don't have a complete quantum theory of gravity, but what we have is a number of interesting research programs that might lead towards a quantum theory of gravity. And the peculiarity is that within their limitations, all of these programs give the same answer for black hole entropy. There are at least three approaches within string theory. There are three approaches in loop quantum gravity. You can look at induced gravity. That's Sakharov's old idea that you start without a gravitational action and induce it by integrating out some heavy fields in your action. You could take that approach and go back and count degrees of freedom of the heavy fields that you integrated out. You can look at entanglement entropy in various forms. You can look at instanton calculations, the original Gibbons-Hawking calculation of black hole entropy, but also, for instance, you can compute the probability of a pair of black holes forming, a pair of charged black holes, for instance, and compare the phase space to the phase space of a pair of point particles forming, and you get a phase space that's larger by e to the entropy. Now, some of this is clearly sociological. If I have a proposal for quantum gravity and I calculate the black hole entropy and I don't get a quarter of the horizon area, I'm less likely to publish that calculation. But if you completely discount that, the fact that these approaches all can give you the correct answer, or the standard answer, is again a puzzle. Okay, so let's start with the area law. There's an obvious guess that goes back in some sense to to Bekenstein's first paper on black hole entropy, which is that perhaps the entropy really counts states that live on the horizon, some kinds of edge modes or some kinds of boundary modes that uniquely determine the interior. Now, this is at best a piece of the answer. When Wheeler first suggested to Bekenstein to look at black hole entropy, he famously asked, what happens to the entropy of the universe if I drop my cup of tea into a black hole? So even if you have this answer that there are horizon states that give you the black hole entropy, you still have to ask, how does the entropy of Wheeler's cup of tea somehow get either distributed on or copied onto the horizon rather than simply falling through into the interior? That's an open question. On the other hand, there is some pretty good evidence that black hole entropy comes from horizon states. And this comes from the BTZ black hole, the Bagnatos-Teitelbaum-Zanelli black hole, which was discovered in 1992. This is a black hole in 3 space-time dimensions. I've written down the metric for the BTZ black hole just to show you that I can. It depends on a mass and a spin. It's a black hole in any sense that you would want to define a black hole. It has an event horizon. It obeys the standard classical laws of black hole dynamics. But more important for this talk, you can take any of the methods that are used to calculate Hawking radiation or black hole entropy, apply them to the BTZ black hole, and you get the answer of a quarter of the horizon area. In this case, the horizon is one-dimensional. The spatial section of the horizon is one-dimensional, so the area is the circumference, but that's the right answer. So this is a normal black hole in most senses. But in 2+1 dimensions, there are no local degrees of freedom in pure gravity. There are no gravitons, no gravitational waves, no local fluctuations of the metric. So if BTZ black hole entropy is to be explained by anything, it has to be some sort of extra boundary or edge degrees of freedom. So the first attempt to answer this came from work by independently by Strominger and by Birmingham, Sachs, and Sen in 1998. So this is a 25th anniversary of this. What they pointed out is, first of all, the BTZ black hole is asymptotically anti-de Sitter. This is just a property of 2+1 dimensional gravity, that there are no black hole solutions unless there's a negative cosmological constant. That means that asymptotically, the asymptotic boundary of the BTZ black hole looks like a cylinder. Whoops, wrong direction. The asymptotic symmetries of such a cylinder, of such a three-dimensional spacetime with a cylindrical boundary, are two-dimensional conformal symmetry. This was already discovered by Brown and Hainaut in 1986. It's probably the first example of an ADS-CFT correspondence, although it wasn't presented in that way at the time. So you have an asymptotic symmetry, which is a two-dimensional conformal symmetry. As I'll explain in a little bit more detail later, such a symmetry is strong enough that it determines the asymptotic density of states, or the entropy, in terms of just a few parameters of any particular solution. Those parameters were found by Brown and Hainaut in 1986. And what Strominger and Birmingham, Sachs, and Sen realized said you just take those parameters, stick them into the formula for the asymptotic density of states, the Carty formula, and you get out the correct entropy. Now, I have to say that I'm a little embarrassed every time I talk about this, because Brown and Hainaut did their work at the University of Texas in 1986 while I was a graduate student there, and Hainaut was one of my professors. In 1995, I wrote a paper that said, hey, if we want to understand the BTZ black hole entropy, there's this formula, the Carty formula, that gives the density of states in a two-dimensional conformal field theory. If only we knew the right parameters, we could work out the density of states, having forgotten that Brown and Hainaut worked this out while Brown was a fellow graduate student. But so Strominger and Birmingham, Sachs, and Sen found it. So that's fine. That's what matters. So the problem with this is that it appears to be unique to the 2+1 dimensional black hole. Two-dimensional conformal symmetry is much, much stronger than conformal symmetry in higher dimensions. The group of conformal transformations is infinite dimensional in 2 dimensions. It's finite dimensional in 3 dimensions. So there isn't an analog to this in higher dimensions. So the question is whether it's possible to generalize. Well, there's one generalization that was immediate already in 1998, which is that for a certain class of black holes, near extremal black holes, the near horizon region looks like the BTZ black hole times some fairly trivial additional dimensions. And so you can dimensionally reduce to a BTZ black hole near the horizon, do the same calculation, and you get the right entropy. But those are still exceptional cases. It's not at all generic. In 1999, Solodukin and I independently suggested that maybe there's some way of finding a preferred two-dimensional subspace of a higher dimensional black hole, in which case you could use exactly the same methods. This was carried out in a beautiful way in 2009 for the extremal and near extremal Kerr black holes by Strominger and his students. But again, this was a special case. More recently, based on work that I'll talk about in a few minutes, I propose that maybe there's a different two-dimensional symmetry that does the job. We're certainly not there yet, but this seems like a promising place to look. So why is there hope that this might make sense? For this to work, we need either at the horizon or somehow at infinity, we need to have something like a two-dimensional conformal symmetry. So why conformal to begin with? There's potentially a good answer, which is that for an observer who's stationary outside of a black hole, any scale-dependent degrees of freedom, things like masses or dimensionful coupling constants in a field theory, get redshifted away as you approach the horizon. This has been used to derive Hawking radiation for matter by looking at an effective two-dimensional conformal description of the matter, or a higher dimensional description, but with a two-dimensional conformal symmetry. So perhaps it's reasonable to hope that this can extend beyond matter field theories to the full gravitational theory. So why two dimensions? What's special about two dimensions? Well, there are a couple of possible answers to that. For a stationary black hole in 4 dimensions, there are 2 killing fields, 2 killing vectors at the horizon. And that gives 2 dimensions, basically a time translation and a rotation. Those are what were used to form this Kerr CFT correspondence. But that's a little bit of a special case still, because in higher dimensions, there are more than 2 killing vectors for a stationary black hole. However, there's another sense in which there are 2 preferred directions at a horizon. One of them is a sort of obvious one. A horizon is generated by null geodesics, basically the paths of light that is of photons that are trapped exactly at the horizon. That gives a null direction that is along the horizon, though also because of peculiarities of null vectors, it's also normal to the horizon. So the null normal of the horizon gives you one preferred direction. And then there's a second direction, which is the direction basically orthonormal to the horizon, pointing outward. So those 2 define a preferred 2-dimensional space. You can think of it as the RT plane, where T is time along the horizon, R is the radial direction. Alternatively, you might hope to get by with just one preferred direction, which the horizon generator gives you. If you have a holomorphic restriction of a conformal symmetry, that's essentially a one-dimensional symmetry, and also gives you control over the density of states. On the other hand, the real reason to look for 2 dimensions, to be honest about this, is that maybe we're lucky that there is this possibility of two-dimensional symmetries determining black hole density of states. So let's see if it can work. So let me step back for a minute and say a little bit about two-dimensional conformal symmetry, about the symmetry that I'm talking about. Sorry to keep pausing, I'm just getting over a cold. So in 2 dimensions, the metric can be written in terms of complex coordinate z, and you can choose coordinates so that the metric is the line element is just gz z bar dz dz bar. In that form, there is an obvious diffeomorphism symmetry, which is simply sending z to a function of z and z bar to a function of z bar. If you don't simultaneously transform the metric, then the metric gets multiplied by an overall positive factor. So these are somewhat sloppily called conformal transformations. Technically, they're diffeomorphisms, and conformal transformations are something mathematically slightly different, but that's a fight that's been lost. The terminology is established in physics. Now, the point is that these are an infinite dimensional symmetry. F and F bar can be arbitrary holomorphic functions. The infinitesimal version is just to shift z by an infinitesimal function of z and z bar by an infinitesimal function of z bar. These diffeomorphisms will have generators, which are typically denoted by capital L for the holomorphic part and capital L bar for the anti-holomorphic part. Those generators obey a simple algebra, which is called the Virasoro algebra. The commutator of 2 generators, I'm just looking at the holomorphic part here, but the anti-holomorphic part is the same, just put bars on everything. So the commutator of 2 generators is first the standard thing that you would expect from commuting 2 diffeomorphisms. The commutator of a diffeomorphism xi and eta is just eta xi prime minus xi eta prime. Just take a vector, transform it by one diffeomorphism and then by another, then do it in the opposite direction, take the difference. This is what you get. There is a possible additional term, central term, or a conformal anomaly, which doesn't depend on the fields in the conformal theory. It just depends on the parameters that label the diffeomorphisms. You can check that this gives you a consistent algebra, that is, that it obeys the Jacobi identities, and it can be shown that this is essentially the only deformation of the diffeomorphism algebra for one dimension that gives you a good closed algebra. The constant C is called the central charge. It can come from various places. It can come in the quantum theory from quantum corrections, from operator ordering corrections. But also in a classical theory, you can have a classical central charge that comes when you have a manifold with boundary. That comes, I'll talk a little bit more about this in a couple of minutes, It comes from boundary terms that you have to add to the generators of the diffeomorphisms. So we have the central charge, and we also have a set of conserved charges that are analogous to entropy, which are just L naught and L bar naught, the zero modes of these generators. These correspond to shifts of Z and Z bar by constants. Time is basically a linear combination of Z and Z bar, and the angular direction is a different linear combination. So the way to think about these is that L0 plus L0 bar is basically an energy. It's the charge associated with shifts in constant shifts in time. L0 minus L0 bar is angular momentum, the conserved quantity associated with rotations. What Carty showed in 1986 is that if you have a conformal field theory obeying a few technical conditions, that's either at a temperature T or a weight delta. Weight is just the eigenvalue of L0. Then its entropy asymptotically at high energy or high temperature is completely determined by the central charge and the temperature or the weight of the states that you're looking at. This is universality. This is a situation in which you can have conformal field theories describing completely different sets of fields. But if they have the same central charge, the asymptotic density of states is the same. Now, for a long time when I talked about this, I used to say that two-dimensional conformal field theory is the only case that we know in which there is this kind of universal determination of entropy. Excuse me. But a few years ago, it was shown, well, in 2013, so this is again an anniversary, 10th anniversary, Bakshi and collaborators showed that there's another two-dimensional symmetry called BMS3 or Bondi-Metzner-Sachs 3 that also has a Carty-like formula that determines the density of states. BMS, the Bondi-Metzner-Sachs group, is the asymptotic symmetry group of asymptotically flat spacetimes. And this Carty-like formula was originally discovered in the context of asymptotically flat three-dimensional cosmologies. If you look at the algebra, it's very similar to the Virasoro algebra, except that instead of the two generators now, instead of L and L bar, are L and M. And now there's a cross term in the commutators that has a possible central charge. You can actually obtain this algebra by starting with the Virasoro algebra, taking linear combinations of L and L bar, and then taking a limit. BMS3 also has a Carty-like formula that the entropy is determined in terms of the central charge and the weights, the eigenvalues of the zero modes of L and M. So again, there's a possibility that if there's some underlying BMS3 symmetry, there might also be an explanation of universality. Now, I should pause for a second and give you a warning about all of this. First of all, the Carty formula is only an approximation. It's an approximation that for which higher order corrections are fairly well understood. But if you look at very fine detail, it becomes a very bad approximation, because a conformal field theory is typically has discrete states, while the Carty formula gives you a continuous density of states. So if you look at high enough resolution, instead of a nice smooth curve, you'll find a series of very sharp spikes. That might be important for understanding the complete microscopic details of black hole entropy, including in the three-dimensional BTZ case. A lot of us hope that it is, because even though we have this nice derivation of the BTZ black hole entropy, so far it's been extremely hard to find an actual conformal field theory that gives that density of states. There's one candidate called Liouville theory, which is a continuous conformal field theory. It has a continuous set of states. The problem is that there are two different sectors of Liouville theory, and the relevant one, which is called the non-normalizable sector, is very, very badly understood as a quantum field theory. The naive attempt to construct a conformal field theory by just looking at the asymptotic behavior of the BTC black hole gives you a partition function that is non-physical, that has some contributions with negative probabilities. There is a lot of work going on about how to correct that. Should you add additional states that correspond to point particles inside a black hole, for instance? It's an interesting open area of research, but it's definitely open. The other thing that I should say while I'm giving warnings is that while the Carty formula is fairly straightforward to derive, the derivation is really quite unintuitive. The basic idea of the derivation is that if you go back and look at this cylinder at asymptotic infinity, well, forget about it being at asymptotic infinity, just take a conformal field theory, put it on a cylinder where the vertical direction is time. If you want to understand the theory at finite temperature, you make it periodic in time. That is, you identify the bottom and the top circles of the cylinder to make a torus. Such a torus has a set of discrete symmetries, the modular group or mapping class group or the group of large diffeomorphisms. One of those is to simply interchange the two circumferences. So interchange your angular direction and your time direction. You still have the same geometry. If you think about that, what that does is to interchange high energy and low energy states. And this allowed Carty to give, to get information about the behavior of the high energy density of states in terms of the low energy states, which are much better understood, the vacuum state in particular. So this is a very clever derivation, but it is also a little bit unsatisfying. It would be nice if we had a derivation that simply said, here's a conformal field theory, here's a way of getting at its density of states, rather than having to detour through the thermal partition function and some sort of unintuitive transformation of that and then back to the density of states. It's possible that something like the Carty formula can be obtained by looking carefully enough at the Faddeev-Popov determinant for a conformal field theory, which is another measure of the density of states. I haven't gotten this to work yet, although I can get temptingly close, but we'll see. Okay, so can we generalize this to higher dimensions? Well, let's start with the starting point for higher dimensions, which is the Hamiltonian formulation of general relativity. So you start with the metric in ADM formalism with a standard set of canonical variables. Qij is the spatial metric on a constant time slice. Pi ij is the conjugate momentum. You write the Einstein-Hilbert action in Hamiltonian form, and you find that the action is a totally constrained action. That is, that the Hamiltonian consists of a set of constraints, script h and script hi. If we're in d dimensions, I wrote this in 4 dimensions, but it works in arbitrary dimensions. Script h is the Hamiltonian constraint. It is essentially the generator of time translations. The d-1 script hi's are the diffeomorphism constraints or momentum constraints. Those are the generators of diffeomorphisms of the spatial slice at constant time. And together, they generate what are essentially the diffeomorphisms. So this is a constraint system, and as usual in a constraint system, the constraints generate the symmetries. Strictly speaking, what I said is a lie. What is true is that these generators generate a set of transformations called the surface deformations. These are equivalent to diffeomorphisms on shell. That is, they're equal to diffeomorphisms plus terms proportional to equations of motion. In a Hamiltonian formalism of this sort, you should expect that, though, because the diffeomorphisms involve time derivatives, and the Hamiltonian formalism is defined just on a spatial slice of constant time. In any case, this is where you begin. You have a set of generators of symmetries, although I'll argue a little later that there's one other approximate symmetry that might be important. But let's start here. We have a set of symmetry generators. How do we construct a two-dimensional conformal theory that we can use the Carty formula on? Okay, so here's how you do it in 5, I should have put easy in quotes, steps. The first thing you have to do is identify appropriate boundary conditions. You have to do this if you're asking for a question about black hole, if you're asking a question about black holes, because somewhere in the formalism, you have to put in the fact that you're talking about black holes. If you just look at the symmetries of a completely arbitrary space-time, there's no possibility that you'll get the density of states for a black hole because you haven't told the theory that you want a black hole. So in the Hamiltonian formalism, the natural way to put in the presence of a black hole is to introduce boundary conditions either at the horizon or at infinity, and I'll come back to that. Once you have a boundary and boundary conditions, you have to go back and revise your transformation generators by adding boundary terms. The Poisson brackets, or the commutators of two of these generators, gives you a third generator up to terms that you get rid of by integration by parts. But integration by parts gives you boundary terms. And unless you have made a remarkably good guess of what the boundary conditions should be, in general, you'll need additional boundary terms added to the generators to cancel off the terms that you get from integration by parts. So if you now look at the Poisson brackets of two of these modified generators, you'll get a third generator from the fact that your original generators had the right brackets. But in general, you'll get an additional term, a central term, coming from the fact that the Poisson brackets with boundary terms will generally give you a different boundary term and not just the boundary term of the commutators. So there's a general central term that you can calculate, again, in extreme generality. You can now go back and ask if there's a preferred subgroup that's diffeomorphism of a single circle or of two circles, which would give you a Virasoro algebra, or a preferred BMS3 subgroup. Restrict to that subgroup and read off the central term. If it's a consistent restriction, that is, if this is a real subgroup, there's only one possible form that the central term can take, because there's only one possible form of a central extension of a one or two-dimensional diffeomorphism group. So that gives you a central charge, and you already have the Hamiltonian, which gives you the zero modes, and so then you can just count states. So that's the general setup. It is, of course, much harder than that. First of all, you have to decide what boundary and what kinds of boundary conditions you're looking at. There are results for boundary conditions at infinity. That's where the original BTZ state counting came from. There are results for boundaries of a near horizon region. There are results in which you put the boundary at the horizon itself, although actually it's a little tricky. In practice, you put it at a stretched horizon, at a surface just outside the horizon, because the horizon itself is null, which means that points at different times on the horizon are in causal contact, which means that the constraints get much, much messier. And there ought to be something possible now to be done with that that's understood better in the past few years, but it hasn't been done yet. Now, for the BTZ black hole, the boundary conditions were at infinity, but that didn't matter because there were no propagating degrees of freedom in the interior. And so you can actually bring the boundary back in from infinity to any finite distance away from the horizon and do the same kind of calculation and get the same answer. For a black hole in higher dimensions, this is trickier. It's less clear that boundary conditions at infinity are going to capture exactly the details of a particular black hole. In particular, suppose you have two black holes in the space-time. The boundary conditions at infinity, it's probably possible, but very tricky to sort out from boundary conditions at infinity what states go with which black hole. So boundary conditions are hard. Finding an appropriate two-dimensional subgroup is hard. There are a bunch of candidates, as I said earlier. It would be nice to have a much stronger physical argument that said of one of these candidates that this is really the right one. It may be, though, that that's the wrong thing to look for. It may be that there are many different one-dimensional subalgebras or two-dimensional subalgebras that give you the same density of states, and that it's just different ways of looking at the same physical system. There is a subtlety which has to do with moding. The Carty formula is really defined on a circle rather than a line because the components are given as Fourier modes. The horizon is not a circle. The generators of a horizon give you a straight line. And so choosing what kind of periodicity to impose gets a little tricky. And then finally, if you can do all of this, it's just the beginning, because there's a whole rest of black hole thermodynamics beside the entropy that ought to be explained. And if this setting explains the entropy, it ought to be possible to extend it to explain Hawking radiation, for instance. Okay, let me take a couple of minutes to give you a specific example, just to wave some equations and pictures at you. If you start with an arbitrary black hole, as I said, there is one way of picking two preferred directions is to pick the generator of the horizon and a radial direction, a direction orthogonal to the horizon. If you do that, then near enough to the horizon, you can dimensionally reduce general relativity, the Einstein-Hilbert action, to a two-dimensional theory. You get a Penrose diagram that looks like this. The horizon and future null infinity together give you a Cauchy surface. There are two null directions, one along the horizon and the other orthogonal to that. And the dimensionally reduced Einstein-Hilbert action is basically just a two-dimensional dilaton gravity action. So if you look at the symmetries of this action, don't worry about the details here. There's one obvious exact symmetry, which is the diffeomorphisms that preserve the horizon. That is, diffeomorphisms along vectors that are in the direction of the horizon. And you can extend those off the horizon in any way you want. There's another approximate symmetry, though. That has to do with the fact that the curvature and the dilaton itself are constant along the horizon. That's pretty much the definition of an isolated horizon. The dilaton corresponds to the area. An isolated horizon has a fixed area. and the geometry, the curvature along the horizon remains constant. If you change the dilaton by a shift that is a derivative along the horizon, then you can integrate by parts and move all of those derivatives onto the dilaton and the curvature. There's zero at the horizon. And so what you get is a variation of the action that's zero at the horizon, that's not zero off the horizon, but can be made arbitrarily small by having this shift in the area just die off very fast away from the horizon. So that gives you an approximate scale symmetry. And if you work out the algebra of that symmetry and the diffeomorphisms, the horizon diffeomorphisms, you find that you have a BMS3 group. And it has a calculable central charge, and you can use the generalized Carty formula that gives you the right entropy. And it does this in a context that no longer depended on what black hole you chose, because you can do this dimensional reduction for any black hole. But it does depend on this idea of an approximate symmetry that gets arbitrarily good near the horizon, that needs to be understood formally much better. Okay, so I have two more slides and a couple more minutes, couple of brief general physical points. What are the states that are being counted here? Normally, when you have a constraint and you're quantizing a theory, your condition on the physical states is that the constraint annihilates the physical states, because the constraint generates gauge transformations, which shouldn't be physical. If the Virasoro algebra has no central charge, then that's fine. If it has a central charge, then this is not consistent. The central charge is an anomaly. It breaks this. What that means is that you have to weaken these constraints, typically, for example, by only requiring that the positive frequency parts of the constraints annihilate the states, or that the constraints are the matrix elements of the constraints are zero. But what this means is that some of the states which you used to say were non-physical, were just gauge transformations, now have to be allowed to be physical states. These are essentially what the Carty formula is counting. There's an analogy with Goldstone bosons, in which if you have a broken symmetry, then you get a set of different vacua and a degree of freedom that tells you how to move from one vacuum to another. This is essentially the same idea. The horizon, the constraints that there is a horizon break diffeomorphism invariance, and it means that states that otherwise would be identified as diffeomorphism equivalent can become independent. Finally, what I've given you is a very general proposal with a few particular applications which look pretty good, but none of them has really closed the case. How do we tell if this makes sense? Well, first of all, if you come back to that third puzzle that I talked about at the beginning, the fact that so many different approaches gave the same answer for entropy, if the explanation is the symmetry, then the symmetry should be hidden somewhere in those derivations. And there are a few cases where I know how to show this, but there are many others where I don't. There should be an effective boundary, a theory of boundary degrees of freedom induced from general relativity that should tell us more about these degrees of freedom. It should be possible to couple those degrees of freedom to matter degrees of freedom and to connect this to Hawking radiation. And perhaps then, if we have a conformal description of black hole entropy and a conformal description of Hawking radiation, we can describe black hole evaporation in terms of some flow of central charge from the black hole theory to the Hawking radiation theory. These are all hopes for the future, but that's a good place to end. So thank you.
Well, thank you very much. Let's thank Steve for that very nice talk. So we have a few minutes for questions, and be happy to take any. That looks like Jan is already raising his hand.
Hi, Steve. Thank you for the lecture. Very nice lecture. I have a comment concerning general comment concerning the entropy that we counted by the area and not the volume. I mean, isn't it somehow naively, very naively, let's say, expressible by the holographic principle that we should concentrate on the surface and not on the volume? I mean, it's from some naive point of view, it's understandable what I mean.
Sure. My own perspective on that is that on the one hand, it's certainly correct in the sense that we have a great deal of evidence for the holographic principle, but also that in some sense it's assuming the answer because the original evidence for the holographic principle was that black hole entropy depended on area. So if you like, I guess I would say I'll accept that argument if you can show me from some other set of first principles why the holographic principle is right.
Yeah, thank you.
Which I would love.
Any other question? Oh, sorry, go ahead.
It may be that there's something deep in quantum gravity that gives you back the holographic principle. The fact that the constraints are that the Hamiltonian is only non-zero at boundaries and that there are no local observables and things like that. But there isn't a really satisfying derivation that I know of.
In other words, you are wondering why the holographic principle holds, actually.
Yeah, right. Yes, I mean, that's basically what that first question was.
Well, so if are there any other questions? We are running a little short on time, but we could take another quick question if there is one. And if not, then why don't we thank Steve again for the talk?
One question, perhaps.
Oh, yeah, please.
Yeah, sorry. So just related to that last point, how to derive the holographic principle from using other ways than assuming it based from the area law. So isn't there the work from Cassini in 2008, who attempted to give an account of the Bekenstein entropy bound using quantum field theoretical calculations? And didn't he succeed to give an understanding of this effective sphere that Bekenstein was posing in his 1981 paper in terms of Lorentz boosts? So wouldn't that for you count as evidence for the Wittgenstein entropy bound? And then from the Wittgenstein entropy bound, one could at least motivate the holographic principle, even independent of the area law.
Okay, I haven't looked at that paper in quite a while. I don't think that the Wittgenstein bound by itself is enough to demonstrate holography, although I would agree that it is a piece of evidence in that direction. I mean, I think there are lots of other pieces of evidence for holography as well these days. But I don't know of if something like holography is true, it's telling us something very deep about the nature of our physical universe. And I don't know of an argument at that level of depth as opposed to pieces of evidence that perhaps this is correct.
Okay. Mm-hmm.
Of course, I'm very ambitious here, or I'm ambitious for other people.
Oh, okay, then yeah, let's thank Steve again, and yeah, for the wonderful talk. And I believe